Hello everyone and welcome back. Now in this lecture we're going to talk about exact equations, and we're actually going to introduce an upgraded version of integrating factors. So what we're going to focus on in this lecture is how we can solve various other specific nonlinear ordinary differential equations. Like what we've been doing throughout this past few videos, we're going to focus exclusively on first order differential equations. And what I'm going to show you is a powerful method for tackling or solving very complicated, at least looking, differential equations. Now, just like I do with all the lectures, I want to start with an example. I want to motivate up some ideas. Now, here's the equation I want to start with. I'm going to say, I'm going to ask you to solve this thing. So this differential equation is 2x plus y squared, and I'm going to write it in a sort of weird form. If you want to, you can rearrange and solve for y prime to write it in the normal first order linear differential equation form. But I'm going to write it like that for now. And I'm going to walk you through a method of solving this thing, and you're going to feel like everything is sort of coming out of left field. And I'm going to explain it at the very end how all this sort of fits together. But the first thing I want you to notice, this thing is nonlinear, of course, and it's non-separable. Okay, so far the only method we have for solving nonlinear differential equations is identifying if they're separable and using separation of variables. So we can't do that, so we got to do something new here. But note, well, this function, I'm going to call it psi of xy. If I define this thing to be x squared plus, what is this, xy squared, well, this thing satisfies. So again, I'm going to explain to you where this function comes from in a moment. Bear with me though, I want to show you why this function is interesting to me. If I take a partial derivative of this function, what does it look like? 2x plus y squared. That kind of looks familiar, doesn't it? That looks like this thing right here. Is there another piece that might look familiar? Well, let's take another partial derivative. If I take a partial derivative with respect to y, well, now I get 2xy. Interesting. Okay, so clearly this function has something to do with the differential equation. First and foremost, because I gave it to you. Second, because when I take these partial derivatives, I get the pieces of my differential equation here. So what does this actually mean? Well, the differential equation becomes, so the dE becomes, well, I could rewrite that whole thing as psi sub x. This is just partial derivative notation for psi with respect to x. I just don't want to write these Leibniz notation every time. Plus psi sub y times y prime is equal to 0. And now you're thinking, okay, I mean, clearly something's going on, but I can't quite see it. And clearly Jason wants me to see something here, but it's still a little fuzzy, right? Well, here's the idea. This, if I rearrange for y prime, I can apply my existence and uniqueness theorems as long as I'm not dividing by 0, right? So as long as x is not 0 or y is not 0. Okay, great. So let's imagine that I'm outside of those regions. I have a unique solution. And so if I can write that solution as y equal to y of x, of course, that's what it means to be a solution. So is a solution to the dE differential equation. This tells me that if I put that solution into my function psi, okay, so I replaced y by the particular solution. So that thing only depends on x now. And now, if I take a derivative of that thing with respect to x, okay, so I'm using script d now because that is this is just a function of one variable, x, right? As I move x around, It moves x around inside psi, and it moves x around inside of y. If I take this derivative, this is sometimes called a total derivative. I get psi x plus psi y times y prime, which is equal to 0, just based on the fact that I have a solution to the differential equation. What does that mean? Well, what I did is I identified a function whose derivative is 0. What does that mean? Well, if you think back to your calculus class, functions who have 0 derivative are constant. And so what this means is that if I take a solution of the differential equation and I put it into my psi function, then along that solution, psi is constant. It takes just one value. So, therefore, solutions to the differential equation lie on the level curves. Here we are again. Something we saw with separable equations. That lies on the level curves of psi, which is this, i.e., psi of xy equal to c is the general solution. So just like what we saw with separable differential equations. Remember, we had some function of x and y equal to some constant. And we said that this is a general solution. And if we want to pinpoint a particular solution, we just put in a value for x and y here, determines a level curve that we lie on. And remember, I had all these big, beautiful drawings. Maybe you wouldn't use beautiful to describe them, but I had them. Same thing here. Now, what you can see is that the name of the game for solving the differential equation is now finding psi. So I got lucky, right? You got lucky. I told you what psi is. I knew what it was right off the bat. The question is, how do I find psi? Because that is clearly how you're going to actually solve this differential equation. Well, first and foremost, we refer to psi as a potential function. This is coming from the physics literature, so potential coming from potential energy. So you'll hear me refer to this thing as a potential. So how do we find psi? Well, if we write the differential equation like this. So let's say, consider the differential equation, and I'm going to write it as m of xy plus n of xy y prime is equal to 0. So this is why I wrote it. I wrote this equation in that form, okay? Well, then, by definition, so basically what we can see here, we need psi such that, well, first of all, the partial derivative of psi with respect to x is equal to m. That was this condition right here. And the partial derivative of psi with respect to y is equal to n, which was exactly this condition right here. And if psi exists, we say the differential equation is, let's change the color here to really make it pop. We say this thing is exact. So this is what's called an exact differential equation. It's an exact differential equation if there exists a potential function, that psi function. Okay, still didn't answer you though, right? You still asked me, you said, Jason, how do I find psi, right? Is there any way for me to find it? And I have great news for you. There is a way to tell right off the bat. We have a check to see if you're actually dealing with an exact equation. And if you know you're dealing with an exact equation, then it's relatively simple to identify psi. So here's what I'm going to do. I'm going to give you a theorem. And this theorem is going to tell you how you can check if you have an exact equation. So we've gotten a couple theorems in the past couple lectures. Here's the idea. Let m and n, okay, so m and n, and m sub y and n sub x. Okay, so that is partial derivative of m with respect to y, partial derivative of n with respect to x. Let these things be continuous. Okay, so the same condition we've seen for existence and uniqueness over and over and over again, continuity. On the rectangle, so same thing, they depend on x and y. I need a rectangle. Let's use exactly the same notation. So gamma less than y less than beta. Okay, then what can we say? Then this differential equation, m plus ny prime is equal to 0, is exact if and only if. So mathematician notation right here, IFF. That means if and only if. That means it is necessary and sufficient. If and only if, here's my condition. I'm going to write it in different colors just so it really, really pops out for everyone. If and only if m sub y of xy is equal to n sub x of xy. And that is for all x and y in the rectangle. Okay? So, again, let's take a look at this. We've seen stuff like this before. So first of all, I need m and n to be continuous. We kind of always have to have that, right? Continuity is going to give us solutions to differential equations. Okay, so even if you don't go deep into the proof, you could probably still guess why you need these things, right? Now the question is, why did I give you the partial derivative with respect to y and the partial derivative with respect to x of m and n respectively? Okay, well, one reason is you can see this thing down here. Clearly, it's going to be useful, but there's a deeper meaning here. And the deeper meaning comes from actually the proof. So just before I show you that, let's talk through this again for a second. Okay, so you know why they're here, because they show up down here. But also, we say that the solution is exact. What does it mean to be exact? I just gave you a definition. That definition is if a potential function exists, then you're exact. Okay, so again, if you want to replace this word exact right here with then, the general solution is written as psi of xy is equal to c, if and only if blah, 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 blah. Okay, so why, right? Why that condition in blue right here? Surprisingly, it's actually very easy to see, right? So first of all, psi such that, okay, if I know psi is equal to, if I take the partial derivative with respect to x and it's equal to m, and the partial derivative with respect to y and it's equal to n, well, take another partial derivative, okay? So let me hit this thing with a partial derivative with respect to y. So partial xy is equal to m sub y. Good. Starting to see things that I might have seen before. Similarly, partial yx is equal to n sub x. Now, one of the things you probably learn when it comes to partial derivatives is that you can swap the order. Now, unless you were really, really, really paying attention in class that day, there was something probably that your professor said that you took for granted and you probably emptied out of your head the second you learned it. But you can only swap that order when those partial derivatives are actually continuous. Now, I know that my one partial derivative is equal to m sub y. I know another partial derivative is equal to n sub x. So why did I need to assume these things are continuous? So that I can say that these two things are going to be equal, and therefore these two things are going to be equal. So it's important to sort of pay attention to the details here, right? Continuity of m and n, again, we probably could have guessed. That comes from just guaranteeing a solution to the differential equation. But continuity of these two wasn't immediately obvious. The reason for that is so that we can switch the order of partial derivatives and say that in fact these two things are exactly the same, which sort of by transitivity here tells us or gives us this condition that we needed in order to check a function or a differential equation is actually exact. Okay, let's do an example. Let's actually see this in practice. So let's say, example here, let's do y cos of x plus 2x e to the y plus, now that's going to be my m term, sine of x, and then plus x squared e to the y minus 1, y prime is equal to 0. Okay, so m term right here, n term right here. So what's the first thing that I'm going to do when I'm encountered with an equation that looks like this? Well, I want to check if it's exact or not, right? Because I don't want to start doing a bunch of work and find out that it's not going to work or it's not going to lead anywhere because no such potential even exists. So every single time you start with a equation you think might be exact, you start by checking if it satisfies the equations for being exact. So let's take a look. M sub y. Well, if I take my m function right here, differentiate it with respect to y, again, just a nice, easy partial derivative. 2x e to the y. That's good. N sub x, if I take a partial derivative here, I get cos of x, and then plus 2x e to the y. Good. Equal. These two things are the same, which implies that I've got an exact equation. So that's good, right? That's how you can apply that theorem in practice. You can do this check. And that check says to you, yes, Jason, you are currently working with an exact equation. Now, why is that good? Because that tells me that if I'm working with an exact equation, the name of the game is finding psi, right? Just like what we did with that first example. Okay, so now that we know the equation is exact, now we need to find the potential function. So how do we do that? Well, here's what we know. So now we know that if a potential function exists, it is going to have its partial derivative with respect to x equal to m, which I know what that is. That's cos of x and, y cos of x plus 2x e to the y. I've got a derivative of a function. We know how to undo derivatives. It's just a simple integration. So if I just integrate with respect to x, I get that the potential psi of xy is equal to, now treating y as a constant, I get y sine of x, that's integrating y cos of x, plus x squared e to the y. And you're going to be tempted to put in plus c here, but you have to be very, very careful. This is partial integration. It's coming from partial differentiation. So technically, you could have an entire function of y's kicking on the outside here, right? Because when you take a partial derivative with respect to x, anything that includes a y, or only includes y, gets differentiated to 0 because y gets treated like a constant. So I have an entire unknown function, h of y. How do you find h of y? Well, I've only used one piece of information so far. I also know that if I take a partial derivative with respect to y of my potential, then that has to be equal to n, which, when I take this partial derivative of this equation, my psi right here with respect to y, sine of x plus 2x e to the y, plus x squared e to the y, and then plus h prime of y. That right there, maybe we'll put this underneath. That's psi sub y. All right, so that's taking the psi that's right here, differentiating with respect to y, then this thing is equal to now my function n, which was sine of x plus x squared e to the y minus 1. And so just so you know, this is my actual n function. Okay, good. I've got sine on both sides. I've got x squared e to the y on both sides. And so really, you can see that you get h prime of y is equal to minus 1, which in my case tells me that h of y is equal to minus y. Now here you're wondering to yourself, why didn't you put a constant in? Well, let's take a look. Therefore, my potential psi of xy is equal to, so here's my potential, y sine of x plus x squared e to the y minus y, that's my h term. If that thing had a plus c on the end, remember that the general solution, so and the general solution is psi of xy equal to any constant. So if I put a constant on the end here, I could just bring it over and include it in this constant. I don't like having two constants in here. It doesn't seem like it's necessary. So what I do, I don't worry about the constant. I just care about the functions of x and y that are in here. And then what I can do is just absorb that constant into this piece right here, because the solutions just lie in the level curves. But that gives me a general solution to my ordinary differential equation, to my exact equation that I had on the previous board. Okay, we're rolling with this. Let's do another example. Let me start down here. So here's the example. Okay, I've got 3xy plus y squared, and then plus, so I'm going to organize it for you, x squared plus xy, y prime is equal to 0. Again, I wrote it in brackets so you can easily identify m and n here. It's written sort of in the form that says you should check if I'm going to be an exact equation. And let's do the check. Remember, we can apply that theorem that I had written right here on the previous board. Rewind the video if you need to see it. But that means that all I needed to do was check that the partial derivative of m with respect to y is equal to the partial derivative of x with n with respect to x. M is this term right here, so I get 3x plus 2y. And I get nx is equal to 2x, plus y. This is not equal. Which implies not exact. Now, okay, so it's not exact, right? Does that mean we're done? No, right? Of course, there's going to be a little bit more. Even if you just look at the ticker at the bottom of the video, you know that this thing is going to go on for a little longer. So that should sort of ruin some anticipation. But of course, I'm not one to give up that easy. There's got to be a way that we can solve this. Now, if you look at the title of the lecture, it is about exact equations and integrating factors. Now, the only thing I've spoken about so far is exact equations. So where do integrating factors come in here? Well, let me show you. So integrating factors. So the name of the game here with integrating factors is you want to find mu of x and y. So I'm going to use mu, again, just like I used for the integrating factors for first order linear ordinary differential equations. I'm going to use mu of x and y so that when you multiply it into an equation, mu n y prime is equal to 0 is exact. Okay, so if I could find a function mu that when I multiply it into my equation, it makes it exact. Again, get your teeth sunk in around this equation right here. If I could find a function to multiply in here to make that thing exact, that would be good, right? Because then I could solve it. Then I can just do what I did with the last example, and life is good. Well, okay, that's fine. What is it that I'm going to require out of this, though? Okay, well, if I could find a mu to make this exact, then I could do the same check. Now, what does it mean? This whole piece, mu times m, takes the place of like a new m function. And mu times n takes the place of like a new n function. And so, to be exact, we need, well, what is it that we need? We need that when you take the y derivative of mu times m, this is equal to the x derivative of mu times x. This is just applying my theorem that I had on the board, right? With the new m and the new n after multiplying in the integrating factor. Well, okay, this is a product of functions. Let's open it up. I'm going to open up the derivative, and I'm going to rearrange right off the bat. Okay, so bear with me. Mu of x plus, and what do we have here? Mu y minus nx, mu is equal to 0. So all I did is opened up both of these partial derivatives using the product rule and rearranged it in a way that I thought would be easier to look at. Now, maybe you might disagree with me, but hopefully you'll agree with me by the end of this. Here's the problem. Mu is unknown, and I now have partial derivatives in terms of x and y. This is, again, a differential equation, but it's not an ordinary differential equation. It is a partial differential equation. If you go all the way back to that second lecture where I talked about ordinary and partial differential equations, one of the things I said about partial differential equations is they are very, very hard to solve. And this is no exception. This is a difficult equation to solve in general. So what do? Do we just throw up our hands? No, in some cases, life can be made slightly easier. So here's what I want to try. So if mu is only a function of x, okay? So I want to try and make my life easier. I'm not saying this is always going to work, but maybe sometimes it'll work. If mu is only a function of x, well, clearly mu sub y is equal to 0, right? Just by definition, this thing doesn't depend on y, so therefore it has no partial derivative in y, which means that this equation right here that you're looking at, this piece drops out, and so therefore I essentially get, I'm going to use mu prime because now it's only a function of one variable, is equal to, if I rearrange this, I pull this to the other side, so this becomes m sub y minus n sub x divided by n. That's dividing the n that was right there. I'm just isolating for this mu of x term, assuming this piece is 0, times mu, which, don't be intimidated by all the notation here. This is actually something we can solve because this is really similar. This is like the p of t term that you had for your regular integrating factor. So this tells you that mu of x is equal to e to the integral of mu sub, or m sub y n sub x over n dx. But there's a caveat. The only way that this is going to work is if this thing right here, what's playing the role of p of t, is independent of y. So if this term, my minus nx over n, is independent of y. Okay, that's the only way that this thing is going to work, is if that thing doesn't depend on y. And I'll show you an example in a moment. We're going to go back to this example, but bear with me. Okay, so clearly you can do the same thing. you can say that if, well, in the same vein here, you could have mu as a function of y. Then you can have an integrating factor mu of y, which is equal to e to the integral of, in this case, it's going to be, my minus nx divided by m dy if that thing is independent of y. So same idea, right? Just to sort of squeeze it in, my minus nx over m is independent of x, I'm sorry. Okay, so it's very, very particular scenario. Fortunately, as we're learning differential equations, we are focusing a lot on particular scenarios. So let's go back to this equation and let's try and solve it again, okay? So let's say back to example. Well, what was it that I needed out of this thing? Well, clearly, I want to see if I can get some nice integrating factors without solving this big, ugly partial differential equation. How is it that I can do that? Well, I can check these terms. So if I take m sub y and I subtract n sub x from it, so let's do another check. So it's sort of algorithmic how this proceeds. M sub y minus n sub x. Let's start with this one, divided by n. Well, in this case, I am going to get something very, very nice here. So I get m sub y, 3x plus 2y, minus n sub x, 2x plus y, divided by n, which is x squared plus xy, which is equal to 1 over x. Oh my God, it worked out, right? So this thing is independent of y. So therefore, mu of x equal to e to the integral of 1 over x dx, which is just e to the ln of x, which is equal to just x, is an integrating factor. So therefore, if I multiply x into my differential equation, so now I get 3x squared y plus y squared, plus xy squared. Sorry, I'm multiplying x into both terms here, plus x cubed plus x squared y prime equal to 0 is now exact. So once I multiplied that mu integrating factor into this differential equation right here, now I've got an exact equation. And now, you can check very, very easily that that thing is exact. And you can further check, you can solve it in the same way we did with this. And so therefore, you get your potential function is very simple. In fact, it's equal to x cubed y plus 1/2 x squared y squared. That's your potential function associated to this after you do the work, right? So you got to do the same thing that I did right here, just for the sake of it. I'm not going to bother, but you get your potential function. You know that solutions lie on the level curves of that thing. The general solution is psi of xy equal to a constant. Beautiful, right? Now, here's the weird thing. Just before we close up on this, what I want you to notice is that, this was a fairly arbitrary choice to try and say, well, maybe it doesn't depend on, x or y, my integrating factor. It works out because I get an easier thing to solve, and it kind of reduces back to integrating factors that we worked with in just ordinary differential equations and non-exact equations, just those linear equations. So that's okay, we can get some results here. But technically, you can find integrating factors if you're able to solve this partial differential equation in general. Now, I am not saying that's easy. I am not even saying that I can do that. But technically, it could probably be done. And in fact, there's more than one integrating factor for this equation. You could also find that mu of xy equal to 1 over xy times 2x plus y. Okay, so very, very complicated looking function. Technically, that function is a solution to this partial differential equation using this m and this n. So complicated. Technically, that's a solution. Technically, I'm going to leave this for you to check on your own. If you put that function, if you multiply it into this differential equation, it also makes it exact, and then you can solve it. So what I want you to take away from this is that we can try and restrict our search for integrating factors, and by doing so, sometimes they can be found, sometimes they can't. But if they can be found, then it's pretty easy, right? Now it sort of starts to look a lot like what we did with integrating factors before. But technically, the general theory here is that integrating factors come from a partial differential equation. Partial differential equations are very hard to solve, right? We're still only really learning how to solve ordinary differential equations. So we're not even there yet. But if you could do it, for example, you could get something like this, then you could find another different integrating factor, right? So there's multiple integrating factors for this equation. The last piece that I want to leave you with here is that I'm not teasing you or leading you on and thinking like, eventually you're going to be able to solve this thing. That's not true. This is a very complicated equation, something that I do not, off the top of my head have a way of solving, and especially in complete generality, I do not have a method of solving that thing. So it's not like I'm just hiding something from you here. By doing this restriction, that's about as good as we can get in a completely general situation.